What if the most revolutionary bomber of World War II could slip past radar defenses completely undetected? By the closing months of 1944, Nazi Germany had developed an aircraft that absorbed radar waves instead of reflecting them. This was not science fiction. It was the Horten Ho 229, a jet-powered flying wing that promised to make its operators invisible to the electronic eyes that protected Allied territories. The aircraft could theoretically penetrate British airspace undetected, deliver its payload, and vanish before interceptors could respond. Yet this remarkable machine never fired a shot in anger. It never dropped a single bomb on an enemy target. By the time the first prototypes took to the skies, the Third Reich was already collapsing under the combined weight of Allied armies advancing from east and west. The story of this failed wonder weapon begins not with the aircraft itself, but with the golden age of German air power that preceded it. When war erupted in September 1939, the Luftwaffe represented one of the most modern and capable air forces in the world. Its bomber fleet had been designed and built for a new kind of warfare. These were not the lumbering giants of the First World War. They were fast, efficient machines built for tactical support of ground forces. The Heinkel 111, Dornier 17, and Junkers 88 formed the backbone of this force. Each had been tested in the Spanish Civil War. Each had proven its worth in combat conditions. The early campaigns seemed to validate every assumption about German air superiority. Poland fell in weeks. The bomber formations struck airfields, rail junctions, and communication centers with devastating precision. They operated with near impunity. Polish fighters, many of them obsolete biplanes, could barely touch the fast-moving German formations. When the Wehrmacht turned west in May 1940, the pattern repeated. Norway, Denmark, Belgium, and the Netherlands all experienced the coordinated fury of dive bombers and level bombers working in concert with advancing tanks. France, despite possessing one of the largest air forces in Europe, crumbled in 6 weeks. The Luftwaffe seemed unstoppable. This success bred a dangerous confidence among German military planners. The bomber force that had excelled in short, sharp campaigns was about to face its first real test of endurance. In the summer of 1940, the Luftwaffe was ordered to subdue Britain from the air. The plan was straightforward: destroy the Royal Air Force, achieve air superiority, and force Britain to negotiate peace. What followed instead was the first major defeat of German arms in the war. The Battle of Britain revealed a critical vulnerability in the German bomber force. For the first time, the Luftwaffe encountered a sophisticated, integrated air defense system. At its heart was something the Germans had not fully appreciated. Britain had quietly developed the most advanced radar network in the world. The Chain Home system consisted of towers along the British coast that could detect aircraft at distances of up to 200 miles. This early warning gave the RAF time to scramble fighters and position them perfectly to intercept incoming raids. German bomber crews began to notice the change immediately. British fighters appeared with uncanny accuracy. They seemed to know exactly where the bombers would be and when they would arrive. Formations that had previously operated with minimal fighter escort now found themselves under constant attack. Loss rates climbed steadily. In single raids, the Luftwaffe might lose 30 or 40 bombers. These were losses that Germany, already stretched across multiple fronts, could not easily replace. The radar network did more than guide fighters. It fundamentally changed the mathematics of strategic bombing. The element of surprise was gone. Bombers could no longer slip through gaps in coverage. Every approach was monitored. Every raid was met with determined resistance. The technology that would define the rest of the air war had announced itself. Germany needed a solution, but conventional answers were proving inadequate. Higher altitudes did not help. Night raids reduced losses but also reduced accuracy. Electronic countermeasures showed promise but were quickly countered by British improvements. The bomber force that had seemed invincible just months earlier was being systematically destroyed. Something revolutionary was needed, something that could restore the advantage to the attacker. that something would emerge from an unlikely source. By 1942, radar had transformed from a defensive tool into an offensive weapon system. The British were not merely detecting German aircraft. They were hunting them with mathematical precision. Ground controllers vectored fighters along exact intercept courses. They calculated fuel loads and timing to maximize engagement opportunities. Radar operators could distinguish between bomber formations and fighter escorts by the signal returns. They could estimate altitude, speed, and heading with increasing accuracy. The invisible electronic net that surrounded Britain was becoming more sophisticated with each passing month. The statistics told a grim story for the Luftwaffe. Where bomber losses had averaged 5% in the early war, they now regularly exceeded 10% per mission. Some raids suffered 20% casualties. These numbers meant that a bomber crew had virtually no chance of surviving a standard tour of 30 missions. Morale plummeted. Experienced crews were irreplaceable. Each veteran pilot or navigator lost took with them years of accumulated knowledge that no training program could quickly restore. German engineers attempted various countermeasures. They developed primitive jamming equipment that could disrupt some radar frequencies. They experimented with aluminum strips called Duppel, similar to what the Allies called window or chaff. When dropped from aircraft, these strips created false radar echoes that could confuse operators. The technique showed promise during tests, but when deployed operationally, the British quickly adapted their procedures to distinguish between real aircraft and decoy clouds. The Luftwaffe tried changing tactics. They flew at extreme altitudes where radar coverage was weaker, but this reduced bombing accuracy to unacceptable levels. They shifted to night operations exclusively. This reduced losses but also reduced effectiveness. Navigation became difficult. Target identification was nearly impossible. Bombs fell on empty fields as often as they hit factories. The precision that had characterized early German bombing was gone. Meanwhile, British radar technology continued advancing at a rapid pace. The introduction of centimetric radar in 1941 changed the game entirely. These new sets could be mounted in aircraft themselves. Night fighters equipped with airborne interception radar could find and destroy bombers in total darkness. Ground-controlled interception became so refined that fighters could be positioned within visual range of bombers without the bombers knowing they were being stalked. The Americans brought their own innovations when they joined the bombing campaign. They developed radar bomb sites that allowed accurate bombing through cloud cover. They created electronic identification systems that prevented friendly fire incidents. They built massive radar-equipped control centers that could manage hundreds of aircraft simultaneously. Every advancement made the bomber's job more dangerous. German scientists understood they were losing the technology race. Conventional solutions were failing. Making bombers faster helped marginally but increased fuel consumption. Making them fly higher worked until the Allies developed high-altitude fighters. Adding armor-protected crews but reduced payload and range. Every solution created new problems. The fundamental issue remained. Radar could see everything in the sky. It was in this context of desperation that radical ideas gained attention. Some engineers proposed giant aircraft that could fly above the reach of fighters. Others suggested tiny fast bombers that could slip through before detection. But a small group of designers had a different vision entirely. What if instead of trying to avoid radar or outrun it or jam it, they could make an aircraft invisible to it? What if they could build a bomber that radar waves would simply pass through or around? The concept seemed like fantasy. But preliminary tests with wooden aircraft construction had shown unusual radar properties. Certain shapes seemed to reflect less energy than others. Some materials absorbed radio waves rather than bouncing them back. The implications were staggering. An aircraft that could not be detected by radar would render the entire Allied defense system obsolete. It would be like returning to the early days of the war when surprise was possible and bombers could strike without warning. The race to develop this ultimate weapon had begun. The revolutionary concept emerged from two brothers who had been obsessed with flying wings since the early 1930s. While most aircraft designers focused on traditional configurations with distinct fuselages and tail sections, these pioneers believed the future lay in pure wing designs. They had started with gliders, proving that an aircraft consisting of nothing but a wing could fly successfully. Their early experiments in the hills of Germany had demonstrated remarkable efficiency. Without the drag of a fuselage or tail, these gliders could soar farther on less energy than conventional designs. The brothers had submitted proposal after proposal to the German Air Ministry throughout the 1930s. Most were rejected as too radical. Military officials preferred proven designs from established manufacturers. But as the war situation deteriorated, radical ideas gained new appeal. In 1943, when the call went out for revolutionary new aircraft concepts, the brothers were ready with detailed plans for a jet-powered flying wing bomber. The design was unlike anything in the Luftwaffe inventory. The aircraft was essentially a triangle with no vertical surfaces whatsoever. The cockpit was a small bubble integrated into the center of the wing. The engines would be buried inside the wing structure. Every surface was curved and blended. There were no sharp angles or protruding elements. From above or below, it looked like a boomerang. From the front, it presented an incredibly small profile. Initial wind tunnel tests revealed something unexpected. The shape not only provided excellent aerodynamic efficiency but also seemed to interact unusually with radar waves. The curved surfaces deflected radar energy away from the transmitter rather than reflecting it directly back. The lack of vertical surfaces eliminated the strong radar returns that tail sections typically produced. But the truly revolutionary discovery came from the proposed construction materials. The brothers planned to build their flying wing primarily from wood. This was partly due to material shortages. Aluminum was desperately needed for fighter production, but wood offered an unexpected advantage. It was largely transparent to radar waves. Unlike metal, which reflected radio energy strongly, wood allowed much of the radar signal to pass through. The brothers went further. They developed a special plywood using a glue mixed with carbon dust. This combination actively absorbed radar energy rather than reflecting it. Tests on scale models showed remarkable results. When compared to a conventional metal aircraft of similar size, the flying wing design produced a radar return that was 60 to 70% smaller. This meant it would appear on radar screens at much shorter distances. An attacking force of these bombers might remain undetected until they were practically over their targets. By then, it would be too late for fighters to intercept. The integration of jet engines added another dimension to the design. The Junkers Jumo 004 engines, though still experimental and unreliable, offered speeds that no propeller-driven aircraft could match. Buried within the wing, these engines would push the flying wing to over 600 miles per hour. This was faster than any operational Allied fighter. The combination of stealth and speed would make the aircraft nearly impossible to intercept. The proposed armament was modest but sufficient. Two 30mm cannons would handle any fighters that somehow managed to intercept. A bomb bay could carry 2,000 pounds of explosives. This was less than conventional bombers, but the ability to reach the target undetected more than compensated for the reduced payload. One aircraft reaching its target was worth more than 10 shot down en route. The Air Ministry approved the project for immediate development in late 1943. The designation Ho-229 was assigned, referencing the designers and the aircraft's projected weight. 3 prototypes were ordered initially. If successful, mass production would follow. Factories were already being prepared. Training programs for pilots were being developed. The materials were unconventional, but they were available. Woodworkers could be trained faster than aluminum fabricators. The carbon dust mixture could be produced in quantity. Everything suggested that Germany might have found its miracle weapon. An aircraft invisible to radar, faster than fighters, and producible with non-strategic materials seemed almost too good to be true. Yet the mathematics and the physics were sound. The only question was whether it could be built in time. The development of the Ho-229 immediately ran into a fundamental problem that plagued all of Germany's wonder weapon projects. The program was competing for resources with dozens of other emergency initiatives. The V-1 flying bomb and V-2 rocket programs had absolute priority. They consumed vast quantities of fuel, specialized materials, and most critically, the best engineers and technicians. Fighter production took precedence over everything else as Allied bombers pounded German cities daily. The jet fighter program alone required thousands of skilled workers and massive quantities of special alloys. The Flying Wing project was assigned to the Gotha Wagenfabrik Company for development and production. This firm had experience with aircraft manufacturing but had never attempted anything so radical. They were simultaneously trying to maintain production of conventional aircraft while retooling for an entirely new construction method. The wooden structure required different tools, different skills, and different quality control procedures than metal construction. Workers accustomed to riveting aluminum had to learn laminating techniques and precision wood joining. Material acquisition became a constant struggle. The special carbon-infused glue was not difficult to produce in laboratory quantities. Manufacturing it in the tons needed for production aircraft was another matter entirely. The carbon dust had to be ground to exact specifications. Too coarse and it would not mix properly. Too fine and it became a respiratory hazard for workers. The mixture had to maintain consistent proportions throughout each batch. Variations could create weak spots in the structure or gaps in the radar absorption. The plywood itself required specific types of wood in particular thicknesses. Not just any tree would suffice. The wood needed proper grain orientation and moisture content. It had to be aged correctly and stored in controlled conditions. Germany's forests were already being stripped for construction timber and fuel. Finding quality aviation grade would become increasingly difficult as the war progressed. Allied bombing compounded every difficulty. The Gotha factories were hit multiple times in 1944. Each raid destroyed completed components and killed trained workers. Production lines that had taken months to establish were wrecked in minutes. Even when the factories were not directly targeted, transportation networks were constantly disrupted. Components manufactured in one location could not reach assembly points. Completed sections sat in rail yards that were bombed before shipment. The jet engines presented their own challenges. The Jumo 004 was notoriously unreliable. Engine life was measured in tens of hours rather than hundreds. They required special metals that were in critically short supply. Each Ho-229 needed 2 engines, but engine production could barely keep pace with the conventional jet fighter program. Test engines had to be shared between multiple prototype projects. When an engine failed during testing, which happened frequently, weeks might pass before a replacement arrived. Pilot training for such a radical aircraft design could not begin until flying prototypes existed. Simulators were impossible to create without real flight data. The Flying Wing handled completely differently from any conventional aircraft. It had no vertical stabilizer, making yaw control challenging. The control surfaces were integrated into the wing itself, creating unusual feedback characteristics. Pilots would need extensive retraining, but there was no time and no fuel for extended training programs. Quality control became nearly impossible under these conditions. Each prototype was essentially hand-built by workers learning as they progressed. Specifications changed constantly as problems were discovered. The first prototype was built as a glider to test basic aerodynamics. It revealed significant stability issues that required redesign. The second prototype incorporated jet engines but used different materials than planned for production models. The third prototype was closer to the production standard but was still being modified when construction ceased. By early 1945, it was clear that mass production was impossible. Germany lacked the materials, the workers, the facilities, and most importantly, the time. The Allies were advancing from both east and west. The wonder weapon that might have changed the air war would remain a handful of prototypes. The revolutionary had been defeated by the mundane realities of industrial warfare. The first prototype of the Ho-229 flew as an unpowered glider in March 1944. Test pilots reported unusual handling characteristics but confirmed the basic design was sound. The aircraft needed constant small corrections to maintain level flight. Without a vertical stabilizer, it tended to yaw unpredictably. But it glided efficiently and landed safely. The radical shape that had existed only on paper and in wind tunnels had proven it could fly. The second prototype incorporated two Jumo 004 jet engines. Its first powered flight came in December 1944 at an airfield near Göttingen. The test pilot reported extraordinary performance. The aircraft accelerated rapidly and climbed at rates that seemed impossible for its size. It reached speeds approaching 500 miles per hour in level flight. The lack of propeller torque and the smooth jet thrust made it surprisingly pleasant to fly once pilots adjusted to its quirks. Tragedy struck in February 1945 during the third test flight. An engine flameout caused the prototype to crash, killing the test pilot. The accident revealed a critical flaw in the design. With engines buried in the wings, an engine failure created severe asymmetric thrust. The aircraft became almost uncontrollable. Conventional twin-engine aircraft could compensate with rudder input. The Ho-229 had no rudder. This problem had no easy solution without redesigning the entire aircraft. The third prototype was under construction when American forces overran the Gotha factory in April 1945. They found the partially completed aircraft in an assembly building along with components for several more. The wings were complete. The special radar-absorbing coating had been applied. But the engines had not been installed. Control systems were missing. The cockpit was empty. It was perhaps weeks away from completion when work stopped forever. American intelligence officers immediately recognized the significance of their capture. Here was evidence that Germany had been developing what appeared to be a stealth aircraft decades before anyone thought such technology possible. The prototype was carefully dismantled and shipped to the United States for evaluation. Engineers who examined it were astounded by the advanced thinking it represented. The smooth blended surfaces, the internal engine placement, and especially the radar-absorbing materials were revolutionary concepts. Technical evaluation confirmed what German engineers had claimed. The wooden construction and special coating significantly reduced radar signature. Wind tunnel tests validated the aerodynamic efficiency. The design was fundamentally sound despite its stability issues. With proper development time and resources, it could have become a formidable weapon system. But those were precisely what Germany lacked in 1945. The Ho-229 never fired its cannons at an enemy fighter. It never dropped a bomb on an Allied target. No squadron of invisible bombers ever materialized to strike at Britain or advancing Allied armies. The entire operational history of this revolutionary aircraft consisted of a handful of test flights. One prototype crashed. One was captured incomplete. The first glider prototype was destroyed to prevent capture. Yet the failure was not one of conception but of timing. The Ho-229 arrived when Germany had neither the industrial capacity to produce it nor the fuel to operate it nor the airfields from which to launch it. The designers had solved the technical challenge of creating a stealth aircraft. They had simply solved it 20 years too early and in the wrong circumstances. The invisible bomber remained invisible not because of its special coating but because it never truly existed beyond the prototype stage. The captured Ho-229 prototype became one of the most studied German aircraft in American possession. Engineers at Wright Field in Ohio dissected every component. They tested the radar-absorbing materials and confirmed their effectiveness. The carbon-impregnated glue showed properties that would later appear in modern stealth coatings. The wooden construction demonstrated that non-metallic materials could provide tactical advantages beyond simple resource conservation. American aircraft designers were particularly interested in the flying wing configuration. The Northrop Corporation had been developing similar concepts independently. Examining the German design validated their own research while revealing new possibilities. The Ho-229 influenced the development of the YB-49 flying wing bomber in the late 1940s. Though that project was ultimately cancelled, the knowledge gained fed directly into later programs. The Soviet Union also acquired Ho-229 technical data through captured documents and interrogated engineers. Soviet designers incorporated elements of the flying wing research into their own experimental programs. While they never produced a direct copy, the influence appeared in various experimental aircraft throughout the Cold War period. The concept of radar absorption through materials and shaping became a cornerstone of Soviet military aviation research. The true vindication of the Ho-229 concept came decades later. When Northrop developed the B-2 Spirit stealth bomber in the 1980s, they employed principles remarkably similar to those pioneered by the German designers. The flying wing configuration, the blended surfaces, the composite materials, and the internal engine placement all echoed the 1944 prototype. Modern computer modeling confirmed what German engineers had discovered through intuition and experimentation. In 2008, Northrop Grumman built an exact replica of the Ho-229 using the original specifications. They tested it at their radar cross-section measurement facility. The results were remarkable. The aircraft showed a radar signature reduction of about 20% compared to conventional aircraft of similar size. While modest by modern standards, this would have provided significant tactical advantage in 1945. Detection ranges would have been reduced by several crucial miles. The Ho-229 never changed the course of World War II. It never proved itself in combat. It remained a might-have-been, a prototype of a future that never arrived. Yet its influence rippled through aviation history. Every modern stealth aircraft owes something to those German engineers who asked whether an aircraft could hide from radar. They proved it could be done with 1940s technology. The story of the Ho-229 is ultimately one of vision exceeding capability. The designers saw the future of aerial warfare with remarkable clarity. They understood that detection was the key vulnerability of aircraft and that defeating detection would restore the advantage to the attacker. They were right. They were simply right at the wrong time in the wrong place for the wrong cause. Their invisible bomber became visible only in the influence it wielded on every generation of aircraft that followed.